Okay, well, welcome back to this long unit. I hope you're sticking with me. We're going to talk about the mobile charge in the next two lectures. The mobile charge, this is the mobile electrons for an N-channel MOSFET, the mobile holes for a P-channel MOSFET. These are the carriers, these are the charges that carry the current in the transistor. So we'll talk about mobile charge versus surface potential in this lecture. So our drain current, it's basically our drain current is just charge times velocity. The more charge, the more current. The faster the charge moves, the more current. We have been discussing Q sub S, the charge in coulombs per square centimeter in the semiconductor. All of the charge, whatever it is. We've also discussed Q sub D, the charge in coulombs per square centimeter in the depletion layer due to the ionized acceptors in an N-channel MOSFET or the ionized donors in a P-channel MOSFET. But we need Q sub N for an N-channel MOSFET or Q sub P for a P-channel MOSFET, the mobile charge. And we need that eventually as a function of gate voltage, but first of all, let's understand it as a function of surface potential. So we'll talk about the mobile charge, the mobile electron charge as a function of surface potential in this lecture, and in the next lecture, we'll relate that charge to the gate voltage. All right, here is an MOS structure biased at a positive gate voltage. It may be below threshold, it may be above threshold, but the bands are bent down, so we have more electrons at the surface than we do in the bulk. If we want to evaluate the electron density per cubic centimeter into the depth of the semiconductor, we know that it's related with our usual expression to the location of the Fermi level relative to the bottom of the conduction band. Okay. Now, as the conduction band moves down, that tells us that the potential is moving up. So we can see that the electron density versus position is its value in the bulk, where the potential is 0, times e to the q potential over kT at the location y. N sub b there is the electron concentration in the bulk of this p-type semiconductor. That's a very small number, Ni squared over Na. And we could then ask, what's the electron concentration at y equals 0 at the surface? It's just the concentration in the bulk times e to the q surface potential over kT. That's an important relation. All right, we've been talking about electron densities per cubic centimeter, but what we need is the charge per square centimeter. We need to integrate the electron density versus depth into the semiconductor so that we get all of the electron charge. It's piled up very close to the interface, but we need to integrate over that thin layer into the semiconductor. So we'll do that integration, and our answer will come out in coulombs per square centimeter. Now, what do we expect? Well, the electrons are piling up right near the surface, and they have a negative charge. So we would expect this charge to be something like minus q times the electron density per cubic centimeter right at the surface times the thickness of this very thin layer. Well, we know that the electron density at the surface goes as e to the q surface potential over kT, so we expect this mobile charge to vary exponentially with surface potential. And we'll see that this is not quite right for this bulk system, but it's very close, and we'll explain why in a little bit. Well, let's do that integral. We simply have to work out this integral. We could do a change of variables so that our variable of integration is the potential instead of distance. Doing that change of variables, we introduce a dy d psi, and then we remember that minus d psi dy is the electric field. And we're integrating over a very thin layer. Let's assume that the electric field is approximately constant over this layer that we're integrating, constant at its value at the surface, E sub s, so we'll just pull it out of the integral. That simplifies the integral greatly. Now we have an easy integral to do. We can do it, and the final answer is this. The charge, the mobile charge per square centimeter in the semiconductor is minus Q times the electron density in the bulk, Ni squared over Na, times e to the Q surface potential over kT, times kT over Q divided by the electric field at the surface. If you look at that quantity in brackets, you can see that it has the units of distance. The numerator is volts, the denominator is electric field, volts per centimeter. So that quantity in brackets we can interpret as the thickness of this mobile charge layer, or inversion layer. So that's our final expression for the mobile charge per square centimeter. This expression that we've developed, this is valid above or below threshold. We have to be a little bit careful about the electric field. I'll explain why in a minute. But that's value. Below threshold, we do have electrons there. It's just a small quantity. But they carry the leakage current of a MOSFET. So it's important to understand the electron concentration versus surface potential, both below threshold and above threshold. Okay, so let's look below threshold first. We'll begin with the expression that we just derived. Below threshold, the electrostatics is mostly determined by the ionized acceptors because the concentration of mobile electrons is so small. Well, we can then determine the electric field at the surface using our depletion layer theory. So we have an expression for the electric field at the surface. Okay. Using that expression, we have our expression for the mobile electron charge versus surface potential. And the takeaway from this is that that mobile charge increases exponentially with surface potential. There's a square root of surface potential out front, but that's a slow variation compared to the exponential. So if we were to plot this, what we would just see is an exponential increase as we increase the surface potential. Okay, that's what happens below threshold. Now let's look above threshold, and we have to be a little more careful. We begin with the same expression. Okay. Below threshold, we just use the electric field from depletion layer theory. We cannot do that now because if we're well above threshold, we're dominated by the charge in the inversion layer, the mobile electrons, and the electrostatics is different. We can't use depletion layer theory to deduce the electric field. What we can do is we can use Gauss's law. We can say that the normal displacement field right at the surface of the silicon is equal to minus the charge in the silicon. And well above threshold, the charge in the silicon is virtually all due to mobile electrons. So we can write the charge in the semiconductor is just Q sub n. That's an approximation, but a good approximation if we're well above threshold. Okay, so now that we have the electric field, now we have to just be a little bit careful because we're integrating through a very thin layer, but there is a lot of charge there. And what that means is the electric field is going to change very rapidly and be essentially zero when we integrate to the end of that very thin layer. Well, since the electric field is changing rapidly in that layer, we should use its average value. It's E sub s, it's the value we deduced here at the surface. It's essentially zero at the end of this inversion layer, so we'll just divide by 2. That's the average electric field in this thin inversion layer. Now we can use that average electric field in our first expression, and you'll see that we have a Q downstairs on the right-hand side and a Q upstairs on the left-hand side. We're going to get a Q squared, and when we solve that, we'll take the square root of both sides. And what we will find is that the inversion layer charge goes as e to the Q surface potential over 2 kT. There's a factor of 2 there now. So we have deduced how the mobile charge varies below threshold in the previous discussion and now above threshold. So we have our full description now of these sketches that I've been making. If I look at the charge in the semiconductor, I'm first dominated by depletion layer charge, which goes as a square root of potential. but there actually is some small concentration of mobile electron charge there, which will be important as we discuss transistors, because that is the current that flows when we are in sub-threshold conditions. When we go above threshold, we're dominated by the inversion layer. The inversion layer charge is essentially the total charge in the semiconductor, and that increases exponentially as e to the q surface potential over 2 kT. Okay. So this is, we've done what we've set out to do. I should point out that there is a way to do this problem exactly. It requires a numerical solution to do the full problem exactly. If you want to see how that's done, I can refer you to this reference. I'll also point out we've been discussing a bulk semiconductor. We've been thinking of this as infinitely thick. Well, a real wafer is maybe something on the order of 775 micrometers thick. You know, a depletion layer is some fraction of a micron. The thickness of an inversion layer is even much, much smaller than that. So for all practical purposes, these conventional silicon wafers can be assumed to be infinitely thick. This is the bulk MOS capacitor that we've been discussing. Now, modern MOSFET channel structures are somewhat different. They make use of very thin channels. It might be an extremely thin silicon on insulator structure, where the silicon layer is a very thin layer of silicon, a few nanometers thick, typically now fully depleted, undoped or lightly doped so that it is fully depleted under most operating conditions. Or we may flip that silicon layer vertically. A widely used transistor geometry these days is called a FinFET, where the thin layers of silicon are vertical and a gate is wrapped around as much of those vertical fins as we can. We'll discuss why a little bit later in this unit. But these structures are much different. We cannot assume that the silicon channel, the silicon layer is infinitely thick. Okay. So to sort out what's happening here, let's take a look at a simple model problem like this. A very thin silicon layer, say nominally undoped, with a gate on the top and a gate on the bottom. So this might represent a FinFET with the gate wrapped around both sides of it. Should give us an idea of what goes on there. If we draw an energy band diagram vertically through this structure, from one gate through the silicon to out through the other gate, we'll get an energy band diagram that will look like this. The band gap of the insulating layers is very wide. The band gap of the silicon is about 1.1 electron volts. So we get an energy band diagram that looks like this. We recognize that as a quantum well. There will be some quantized energy states, both in the conduction band and in the valence band, and they'll affect the characteristics. And people who are careful these days, and these effects are becoming sizable enough that semiconductor engineers are careful to account for them when they analyze data or transistor performance. We won't go into that much in this unit, but it's important to know that it's there. Now, we don't have a surface potential, but we have a potential of the semiconductor. Notice that there is no band bending. This layer is so thin and fully depleted that the bands aren't bending. That's our assumption here. So the potential is constant in the semiconductor. Psi sub s will just be the potential of the semiconductor. Now, I want to point out before we go on that there is also quantum confinement in the bulk semiconductor, in the bulk MOS system. And that occurs electrostatically because we bend the bands down, we create a strong electric field which pulls the electrons to the surface and confines them there. So you can see that we have a quantum well to confine electrons there. In this case, it's produced by electrostatics. This, in fact, was the first place in the 1960s where physicists observed for the first time these quantum confinement effects in semiconductor systems. Okay, so confinement there is due to electrostatics. In the fully depleted structure, the confinement is due to the the thickness of the silicon itself, to the structure itself. And the thickness of the confined layer is not changing as a function of gate voltage as it does in the bulk system. All right, let's take a look at this system and ask what is the charge per square centimeter in this system. Well, we expect that the charge is going to be exponentially related to the location of the Fermi level relative to the bottom of the conduction band. Not quite the conduction band, I've written it as EC prime because the lowest energy that the electrons can get to is the bottom of the conduction band plus the energy of the first confined state. So it's in the first subband, but the effects are the same. If we apply a positive potential to the semiconductor, we'll pull everything down closer to the Fermi level, and the electron density will increase exponentially. So the electron concentration per square centimeter in this two-dimensional system will be exponentially related to the semiconductor potential. So let's look at how this works out. Here's our system. If we've arranged things with work functions such that the Fermi level is right in the middle of the band gap when we apply zero gate voltage, then we'll have equal numbers of electrons and holes in this system. If we apply a positive surface potential produced by a positive gate voltage, we will pull everything down in the semiconductor. We'll pull the conduction band closer to the Fermi level, and we will increase the electron density exponentially. If we apply a negative gate voltage and produce a negative potential in the semiconductor, we'll pull the bands up. That'll move the Fermi level closer to the valence band. That will decrease the electron concentration exponentially and increase the hole concentration exponentially. So if we are to plot that, it's very simple. The electron concentration increases exponentially when the surface potential goes positive. The hole concentration increases exponentially when the surface potential goes negative. It looks sort of like the bulk system, except there's no depletion charge. So very similar to what's happening here, but there is no charge to deplete. These structures are fully depleted to begin with. We simply have an exponential variation of the electrons and the holes, but it's e to the q surface potential over kT. There's no factor of 2 in these ultra-thin, fully depleted systems. So to summarize, we have accomplished what we set out to do in this lecture, which was to relate the mobile charge in coulombs per square centimeter to the surface potential in a bulk MOS system or to the potential of the semiconductor in a fully depleted ultra-thin structure. So for the bulk structure, if we're below threshold, we have an expression. The mobile charge is there. It doesn't affect the electrostatics, but it's there, and it carries leakage current, and it varies exponentially with surface potential. Above threshold, it varies exponentially with surface potential, a little bit slower because there's a factor of 2 in the denominator of that exponent. For the fully depleted structure, it varies, this mobile charge per square centimeter varies exponentially with semiconductor potential, both above and below threshold. Now, why is there a difference? Why is there that factor of 2 in the bulk? Well, you can trace it back to the fact that the confinement of electrons in the bulk system is an electrostatic confinement. The higher the gate voltage, the stronger we confine it, and the thinner that layer is, and that ends up producing that factor of 2 for us. Now, the next topic that we need to address, now that we understand how the mobile charge is related to the surface potential, we need to understand how the mobile charge is related to the gate voltage that produced that surface potential. That's what we'll discuss in the next lecture.